So a huge thanks to this session sponsor, Build Equinox. Build Equinox manufactures the SERV smart ventilation system in central Illinois in their 100% solar-powered facility, which right now is undergoing verification of becoming a Zero Energy Hero Award program, which we'll get to a little bit later. The CERV is the first smart ventilation system for residents with active monitoring and control of indoor air quality, measuring carbon dioxide, total volatile organic compounds, VOCs. With the SERV's IAQ sensors, filtered fresh air is delivered to your home when you need it the most. The SERV saves energy with its efficient heat pump energy exchange technology. And not only that, this allows the SERV to actively heat or cool and dehumidify incoming fresh air. This makes the SERV ideal for any climate, whether hot, humid, or cold. SERV Ice connects the SERV online, making it even smarter. This enables online monitoring and control of the CERV from any internet-connected device and provides information on the home's indoor air quality impact on occupant health, cognition, and sleep. Don't just ventilate your home, make your house a healthy home with SERV Smart Ventilation. All right, well, welcome to comparisons of HRV, ERV, and smart ventilation systems. Which is best? This course is approved for 1 hour in continuing education units. And unique to this session, unlike many of our other sessions, is certified for both Passive House, FIAS, that is US CPHC, as well as LEED AP Homes Specific. Along with that, it's an ARI Green, AIBD, AIA HSW, Certified Green Professional, and may be applicable to your local state-based design or contractor license. I am your moderator. My name is Brett Little. I'm the Executive Director here at the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. So I'm very excited to have our presenter back here again, Ty Newell. He's the co-owner and co-founder of Build Equinox and holds a PhD in mechanical engineering. He's retired from the University of Illinois in 2007, and he was the assistant dean in the College of Engineering, having advised 70 master's and doctoral graduate students, and is an emeritus professor of mechanical engineering at the university. He has lectured around the world on indoor air quality, comfort, solar energy, building energy efficiency, and resource conservation, including keynote addresses at the Solar Energy Society of India's 25th Silver Jubilee in Istanbul, Turkey, which I'm to believe is the ASHRAE over there equivalent. Ty lives in a 100% solar-powered home that includes automated fresh air control and rainwater harvesting in Urbana, Illinois. And Build Equinox is located in a 450 square foot facility in Urbana, Illinois, and is also 100% solar powered. And we'll be very excited to be digging into some of those numbers and hoping to get them the zero energy designations. All right, so with that, I will be handing it over to Ty, and thanks for joining us today.
Thank you, Brett. Just one minor correction. Our building here in Urbana is 4,500 square feet, not 450. I don't think Ben or Alex would like to be that close to me. Thank you, everyone, for joining us for this webinar. And as I'm a little challenged for chewing gum and walking at the same time, I'll hold answering questions until the end, but for sure, I'd like to encourage questions and comments and appreciate feedback to help improve this presentation, as well as any questions you have that I can follow up with later. So today we're going to talk about ventilation systems with trying to describe the differences between heat recovery ventilators, energy or enthalpy recovery ventilators, and then smart ventilation systems, which are just now entering the market, at least at the residential scale. And so that's our primary goal for today. I'm the old guy to the left or right, however you want to look at that picture, but Ben, who's in the middle, Ben Newell, is president of Build Equinox. Alex Long is a vice president and co-owner of Build Equinox, and then myself, Ty. We're standing in front of our 3.2 kilowatt 2-axis solar tracker that's part of the solar array at our Build Equinox facility in Urbana. And we also have a 5 kilowatt stationary array. And between the two, our 4,500 square foot Morton building is a Zero Plus building. We, as Brett mentioned, we're supplying information to Green Home Institute and looking forward to being named a Zero Plus building, and hope that this will be a good example for others, that both where we live and where we work, that we can live on our daily allowance of solar energy. And that is our primary mission at Build Equinox. In addition to developing and manufacturing the SERV that Brett mentioned, a smart ventilation system, we do a lot of research and education. And to the left of this slide, our recent Vermont report that describes 13 high-performance homes in Vermont that we quantitatively want to help people understand how buildings are performing, the economics of these buildings, and how we can continually improve our lives. And so I hope you'll dig through our website and look for some of these research reports. I'll also mention, since it's relevant to today's talk, you'll find in our February newsletter, and if you aren't signed up, check that out, but you'll find an article on how smart ventilation helps us reduce the probability or the chance of getting sick, catching the flu or catching colds. And the cost, the annual cost in the United States of influenza and colds, rhinoviruses, and other non-influenza respiratory viruses is significant. It's much more than what we spend on energy for refrigerators and hot water and many other things in our homes. And just better ventilation will provide significant decreases in our getting sick each year. And article from January on particulates and how smart ventilation also provides effective means for reducing particulates in general within our homes. Today's talk then is on smart ventilation in comparison to like HRVs and ERVs. And we'll provide some basic definition of those, but overall we'd like to understand how these fit within ventilation standards and improving indoor air quality, and how this is related to costs related to our health, as well as the cost to properly ventilate a home in terms of our benefit, our improved health, our improved cognition, and the energy costs associated with operating an efficient ventilation system. We'll look at how HRVs, ERVs, and smart ventilators operate in different climatic regions, and try to understand, the dollar value of that, as well as the performance differences of these systems. So whether you're in the Southeast, the Northeast, or West Coast, or anywhere in between, just what climatic variations mean in terms of these systems. And finally, let's think about the future, that ventilation and maintenance of excellent indoor air quality, this is important. We're just at the beginning of forming a way to cost effectively improve our health. And this links into a lot of these other things that you're hearing about these days, such as artificial intelligence, big data, and other rapidly developing technologies. Indoor air quality maintenance will definitely interface and be linked to these things, and it will do so in a way that will all benefit. Current ventilation ASHRAE 62.2 for residences. I was recently at the Efficiency Vermont Better Buildings conference in Burlington, and Martin Holliday gave a very interesting historical perspective. And I don't know if I'm paraphrasing it quite right, but he mentioned that ASHRAE 62.2, another way to look at it, is kind of the worst acceptable ventilation that one might have. It's a minimum. It's not an indoor air quality standard, but it's really formulated on the basis that if you meet ASHRAE 62.2, you should at least be doing okay, but it's not a guarantee that air quality is going to be good. That depends on other things within the home, how much off-gassing, how much pollution generation the occupants are causing, as well as other things around it. And basically, it's based on an odor dissatisfaction, not an air quality. At the level that we need to ensure good air quality, our noses are not good enough for telling us that. And so what we find is that at this level of ventilation, 20% of the population is dissatisfied with the air quality. And that was the threshold that was used historically to define what nominally is the 15, 20 cubic feet per person basis for that underlies ASHRAE 62.1 and 62.2 ventilation. The ventilation standard doesn't account for high pollution events, occupancy changes. Our respiration varies by almost a factor of 10 from sleeping to vigorous exercise activity. So one person under normal, say, office-like activities with 20 cubic feet per minute will result in about 1,000 to 1,100 parts per million of CO2 concentration. And recent studies have shown now that that impairs our cognition, productivity, our brain health, and just very minor increases in exertion, doubles and triples and quadruples the amount of CO2 output of a human. So one human can very easily have an output that's equivalent to about 7 or 8 humans under, say, sedentary or less active conditions. So, so our point is that as far as smart ventilation, that can get us to where we need to be, providing fresh air when we need it. Along the lines of this talk, and I'll try to point out in some different areas, but you know, all the different certifications, they're doing a good job making us aware of what we need to do in building design and building construction that will improve air quality. And so just taking LEED as an example, but also Passive House, both FIAS, Passive House Institute US, as well as the European-based Passive House. They all recognize the importance of maintaining good air quality. At this point, they're more prescriptive, and my feeling is that we need to get to where we are more performance-based with actual, say, energy usage, actual measurement of comfort, temperature and humidity within a house, and actual indoor air quality. And if you look on our site, you'll see some of our attempts to improve, say, an understanding of air quality. But at this point, you know, we're at the beginning stages where putting this into design, and I think the emphasis that, for example, LEED has in environmental quality, as well as energy and atmosphere, and then innovation, that these provide potential and hopefully incentive to increase indoor environmental quality. And I hope that where it will go, and we are seeing these efforts around the country, is where then we'll have more of performance-based. So such as the Green Home Institute building awards, where you submit then, say, a year's worth of utility data to demonstrate that you are indeed net zero or zero plus facility. Let's just talk about high performance homes versus conventional homes. This big cloud of data, these solid data points, and those of you who may have attended some of our other webinars have seen this, and hopefully I hope aren't tired of seeing this, but all those solid dots, those are daily energy data from a group of 13 ostensibly identical homes, manufactured homes in Vermont. And these Vermont homes are excellent, high performance, high quality, durable homes. And these homes, for example, exceed both FIAS as well as European Passive House standards by about 20%. 20% less energy than what's required to be certified by those. And the open square data, that's actually my house, which is a bit larger than these homes in Vermont. And that's monthly average daily data, so you don't see quite the scatter in it. And then these are 5 conventional homes. And what you see here is, for those of you who have been involved in the high performance home field, that this cloud of data, there is absolutely a significant difference between conventional homes and high performance homes, such as mine and then these Vermont homes. So building in this manner of super sealed, highly insulated homes, appropriately windowed homes, this makes a significant difference. What you also see, though, is that since these 13 homes are identical, you can see the impact of non-identical humans. And just as humans use energy differently, they also pollute homes differently. Some of these homes, there's not enough fresh air in the world for the occupants. And others, it's hard to tell they're even breathing in there. And so the way we live, the way we like to live is different, and this is important for us to take into account. I'll mention that the numbers below, 1 and 2, these are references on a reference list at the end of this talk. And so the data has been referenced, and I hope you'll look at a number of the articles and reports that this comes from to see more information. Just looking at the history of homes, where we've been and where we are currently. If we go back to the 1920s, homes were not sealed at all, really. No insulation, single pane windows. And so if you ran a blower door test, getting 30 air changes per hour would not be uncommon. This would be a normal leakage of about 1.5 air changes per hour under normal pressure. As we moved to the 1950s, we started sealing homes up better, really because we started putting insulation in wall cavities, and we started adding storm windows, but still quite leaky by today's standards. And moving to what I view as kind of the boundary where we're seeing a fair fraction of homes that are reaching high LEED certification, good HRV score ratings, Passive House certification, that there's not really a lot of difference between, say, a conventional home built in 2010 and then a super performing home built in 2010. The orange shown here is really the human energy activity. You can see that prior to, say, 2010, going to 1950, 1920, our homes, as far as their energy consumption, hardly even knew there was a human in there. We didn't have all the uses for electricity that we do today, and it was dwarfed by what was needed for some climatic control. And I will point out, this home in the 1920s, while it looks like it has maybe 150,000 kilowatt hours of usage, that home really didn't have that. You would keep the parlor warm, or you'd keep a specified, a smaller space warm, rather than trying to keep the whole house comfortable. And you'd wear jackets and coats and petticoats and other things in the house to stay warm. Going to 2010, There's not really a lot of energy difference, so the energy savings, homes are pretty well sealed under conventional construction, and we're now seeing with not a lot of effort that now maybe a blower door reading of 4 air changes per hour is being achieved. And for those putting some effort into it, regularly folks are hitting 2 air changes per hour and less, all the way down to say 0.6 and below if they're achieving like passive house ceiling levels. The thing that happens though, as this extra effort is put in to develop a more efficient home, is that now human load, and as we saw in that other slide, 13 identical homes with unidentical humans, the human load dominates. And so what I view as kind of this boundary at 2010 is where, with some effort to develop a high-performing home, we're entering the era of where our activities in the home are dominant rather than climate. The other thing that's happened, though, is that as we seal homes up, they become less healthy. Here's a plot. This is showing the normalized air leakage, and I have a reference for this. I think it's on a different slide, but from the data from Persili, showing how the normalized leakage, about 1/20th of the blower door measurement, has changed since the 1890s. And about an air change of 1.5 would be a blower door reading of about 30 air changes per hour, 50 pascals. We've done a remarkable job dropping down to where we are today, and we see where a reasonably sealed home, 3 air changes per hour with blower door versus passive house, where this falls as of 2010. And from here on out, we should just see this flatten out as homes continue to be sealed in this manner, which is a good thing. From our January newsletter, you'll find an article on particulates. And particulates, as well as indoor volatile organic compounds, and these are indoor generated particulates, one's from cooking, one's from things that we do that generate particulates. We shed about a pound of skin a year that become particulates with various health-related problems associated with them. You can see that around 1960, 1970, we started on this upward trail of indoor volatile organic compounds without proper ventilation increasing to undesirable levels, as well as indoor particulates. Somewhere around 1970, 1980 is where the balance of indoor particulates outweighed the amount of outdoor particulates moving into our homes. If we layer on data from the CDC and the National Center for Healthy Homes showing how asthma has changed over the past few decades, we can see that asthma has gone from, say, 3–4% a few decades ago to nearly 9–10% today. And relative to the ratio of indoor VOCs and particulates, that this maps almost on top of each other. This upper point is for an unventilated, a so-called leaky home, but one that is so not super sealed, but air changes per hour of 3. We spend most of our time in our homes too, and by a lot of hours per week. It doesn't look like when we look at other indoor 31 hours per week that we're spending a lot of time at work, say, or at school, but this is the population average time. So those folks who spend their time at home or are not are working at home or are not working, this is averaged in it. So that's why that's below what you might think of as far as number of hours worked per week. Significant number of hours in our vehicles too, and again, not a very healthy environment. Let's look at health costs. If we And we will reach the point where all of our homes are very energy efficient, and we're going to reach that because of economic reasons, along with the motivation that this is what we need to do to have a sustainable environment as well as a sustainable economic basis. When homes are high performance, the solar powered energy costs for about 100 million residences, with roughly about 300 million in our populace in the US. The energy costs will be about $160 billion per year, and about 80 billion will be for people and our activities in the homes, TVs, computers, cooking, hot water, and 80 billion for the climate. These numbers vary depending on if you're in Arizona versus Vermont by, say, plus or minus 20%. But nationwide in the US, this is about what we would expect our energy costs to be. Let's look at the cost of seasonal influenza and colds. This is almost $130 billion per year. Influenza dominating the costs, and unfortunately old people like me were a major factor of that cost. For some reason, when we get sick, it hits us even harder. Colds, similarly, a very substantial number. If we look at the cost of hot water, with today's efficient hot water heaters, supplying everyone's hot water in the US would be about $15 billion per year. An Energy Star refrigerator in all of our homes costs about $5 billion per year. So these numbers really dwarf the costs associated with many of our energy uses. Asthma, as we talked about, afflicts 9 to 10% of the populace, and from CDC estimates, about $56 billion per year. Can we, through better ventilation, reduce this to where we used to be at about 4%? Or can we reduce it even more? And presumably that would be $25, $30 billion reduction in costs. That's money in our pockets. That's money we can do other things with. The big dog as far as indoor air quality, and this is just from very recent results, and if you look at some of our newsletter articles and other reports that discuss this recent research by others at Lawrence Berkeley Lab, at Harvard School of Public Health, Syracuse, and State University of New York. Current ventilation levels are decreasing human cognition productivity by about $1.5 trillion per year, spread across our populace. Just simple changes of more effective ventilation is going to make us more productive and presumably make us more valuable, save us more money. This plot just kind of shows how ventilation, and this is linked to several references that provide you with where these dollars come from and how they're calculated. But providing this kind of basis for a residence, moving from today's ventilation standard that results in about 1,100 parts per million of CO2, that's nominally 15 to 20 cubic feet per minute per person of ventilation. If we double ventilation to about 40 cubic feet per minute per person, that would put us at about 700 to 800 parts per million within a home, and that would be about $4,000 to $5,000 of increased productivity. Now, who's paying you at home? While you might not be getting paid directly at home, your productivity at home very, very much impacts your productivity at work. If you're not making good decisions at home, if you're not getting things done that then carry over to work or are leaving you with worries at work, of course this is going to impact your productivity at work. And so it's very important to be healthy and productive at home because this impacts us everywhere else. And as we think of our children, that for sure we want them to be productive and that their brain is operating at an optimal value as they're studying and learning. And before we talk about ventilation specifically, we need to be aware of simple things that we just need to do that are hurting us and that have absolutely no cost to do differently. For example, floor ventilators. Get the vents out of the floor. You can see my foot over this grate that has some conditioning coils, and some critter has been in there munching on some seeds and that. Blowing air through nests that various vermin are creating is not good for us. And for sure, you don't want to smell what's on the bottom of my shoe. And Florence Nightingale knew this 150 or more years ago. And it's common sense. We should know that now, too. Likewise, we see reports like this. We're told materials are healthy, but they really aren't. We need some means of verification, and smart ventilation is one means that can help us see that what we're told actually, in fact, is true, but also that if something isn't quite what we hoped, that we have a means for at least counteracting it and being able to ventilate properly to take care of any off-gassing that may be impacting us. So let's get on to ventilation and what we can do about it. As I mentioned before, current ventilation standards are odor-based, and so the level that we need to get to improve our health, our cognition, productivity, and sleep quality, our noses can't determine it. And so with modern technology, with the sensors that we have available that are more sensitive than our nose, that we do have the ability now to watch what is happening with our air and take action for it. When we look at HRVs and ERVs, these help us. For sure, some ventilation is better than none. But the problem when these are dumb ventilators that do not actively monitor air quality, is that simply turning a dial to a certain fan speed, you're guessing, and you're going to guess wrong. You're either going to guess too much ventilation or not enough ventilation. Too much ventilation has an energy penalty. Not enough ventilation has a health penalty. And so at this day and age, the same way that we use thermostats to smartly turn our comfort conditioning system on and off, we use thermostats in our refrigerators instead of the old refrigerators of the 1920s and 30s with manual switches, that we use modern controls to take care of things so we can be busy with the things that we'd like to be involved in during the day. What I show here is just one form of, it could be an HRV or an ERV because they are the same device. The primary difference is in what's called the core, the energy exchange or the enthalpy exchange core. In an HRV, in the unit to the left, you can see the HRV here with corrugated heat exchanger core in which air flows down and an opposing air stream flows across the other way. These streams are separated. And when the corrugated material separating the two air streams is impermeable to moisture, then we are only exchanging heat. And so we call that an HRV. And then when the core, such as this one, has a permeable membrane in the corrugations, and this might be a paper-like material, it might be a polymer material, like a Gore-Tex or something like that that's breathable, that we can then pass moisture through from one side to the other. Now, while the energy or enthalpy recovery ventilators that allow moisture to pass through are, say, tuned to be selective to only allowing water vapor through, one needs to be careful, and at this point we don't have good quantitative information on the various cores that are out there to see what else is passed through, whether or not formaldehydes may be passed through, whether ammonia, one of our bioeffluents, one of the things that comes out of us and is prevalent within the pollutants in a home, whether this will move through a core. Ammonia is very similar to water in a lot of its chemical properties. And then just other pollutants. And so more data is needed to be able to understand that. A smart ventilator is one that incorporates sensors to monitor pollutants of different sorts. As Brett mentioned, the smart ventilation system that we manufacture, we monitor CO2 and VOCs. And then because of the type of algorithms that we use for recirculation as well as fresh air ventilation, that we are also able to effectively manage things like particulates within a home. Now, why is it important? Well, this way you have the assurance that you know what the air quality is in your home with these sensors. You can record it. You can archive it. It's impossible to control what you don't measure. And so this quantified ability to control it, it gives you a peace of mind. And a peace of mind is as important as actually having good air quality. And then because it will activate controls to bring fresh air in when needed, that changing occupancy, activity levels, and other pollutant events, it can respond to those and make sure that when you're in the house that it's going to actively take care of it. And then it's energy efficient just because it ventilates when needed, and then when you're not there or not as active, or when it's windy outside and the infiltration level through your house is increased, that it can give you the fresh air that's needed, and then avoid excess energy associated with excessive ventilation. We hear a lot with the work that we do. We monitor a lot of homes for air quality. We often hear that, oh, my home's leaky, I don't need any kind of ventilation. And we find that more often is not true than true. Where leaks occur and where you live are two different things. And then this upper plot, this shows CO2 and VOCs in a home, a very well sealed home, a passive house certified home, that has a ventilator in it. It has an ERV. And for 1 week, the couple was living in the home, and you can see that it very frequently, in the case of CO2, was always above 900 parts per million, the threshold that we'd like to see indoor air quality controlled to, as well as VOCs having excursions. Then they were away for a week, and you can see where someone looking in on their house every now and then appeared. And then they came back, and they were starting to build back up to poor indoor air quality levels. I visited the home. It doesn't smell. I couldn't detect any odors. But it's quite obvious that the level of indoor air quality is not where you desire it to be. This bottom shows what smart ventilation can do. These green bars show periods where fresh air ventilation was on. There's also some fresh air ventilation buried within this, but you can see the activity level. When it would hit this 900 parts per million threshold, there'd be a bit of fresh air ventilation. CO2 and VOCs would regularly intertwine. Here, VOCs are setting off fresh air. Here, CO2 is setting it off. Both are important to monitor and to use for controlling. Another difference with smart ventilation systems, incorporating recirculation is a very, very important characteristic. When you simply pass air through at a constant low flow volume through a house, as we're seeing in many homes. One of the problems is that as, say, this fresh air ventilation load, maybe about 40 CFM, is split among several different rooms, that, say, 8 CFM of 40 CFM for 2 people, while on average this house might be 1,000 parts per million, this room is like fresh air level, this room's fresh air level, this one and this one. And the fresh air that is deposited there and then exhausted from the home, it never came in contact with a human. It never supplied them beneficially with fresh air. Instead, where the people might be, in the bedroom, in the family room, this is only getting about 8 CFM, and at that low flow rate, that region can easily reach 3,000 parts per million of CO2 and equivalent VOCs. And so when we deliver, say, what would meet ASHRAE 62.2 standard, but we don't look at how it's distributed and maintained, we have problems in the regions where we're living. And we have inefficiencies. All this fresh air, if there had been recirculation through the house, could have been used to keep this level low. And that's another characteristic that can be built into smart ventilation systems and should be built in. Particulate levels, if we look at the house air exchange rate, and this is normalized exchange rate, so for example, this 0.4 would be a house with 8 ACH at 50 pascals. And down here at the lower end, this 0.03 normalized leakage. This would be passive house level of 0.6. That with recirculation, it allows us to take air within the house through a filter. And so in addition to filtering the outdoor air that's brought in, we have the ability to filter indoor air. And as I mentioned before, around 1970 was when indoor particulates started to exceed in concentration over outdoor, say, dust particulates coming from the outside. If we just have 40 CFM continuous ventilation through a home with this level of indoor particulate generation and this outdoor level, you can see that we have a significantly higher level of particulates within the home. And then a home without any ventilation, as we seal it, particulates, suspended particulates, airborne particulates just gets to an extremely high and undesirable level. Looking at getting sick, and this is a plot taken from our recent February newsletter article, that the probability of getting sick increases as carbon dioxide concentrations increase. So if we were in a home for 8 hours and looking at the probability of getting infected with a cold, different types of viruses are more or less effective. Influenza is a much more aggressive virus than, say, a cold virus. But if we have 2,000 parts per million of CO2, we can see that we're getting to 50–60% chance of catching a cold in that house in an 8-hour period. We're maintaining about 900 parts per million. We're less than half that probability of catching a cold in an 8-hour period. So let's look at some specific characteristics of HRVs, ERVs, and then a smart ventilation system, and just see psychrometrically how these compare. I'm talking to you from Central Illinois, what we claim is the worst weather in the U.S., although I do have to admit that this week we're having very nice, sunny, spring-like weather. And I know many of you in the West Coast and in the South and in the Northeast are having horrible weather. And so we'll try to share some of this wonderful weather with you as soon as we can. But this is a plot of hourly humidity and dry bulb temperature in Central Illinois in the year 2012. And this red outline shows you just kind of an envelope that encompasses all of these hourly data points. The red are summer, the kind of yellowish orange are fall, the green are spring, and the blue are winter data points. And these two boxes show where most people would say they are comfortable if they're in short sleeves and shirts, and if they're in long sleeves and pants. And you can see that we have a few days where it's pretty nice and we feel comfortable outside in those conditions, and then many days that are outside of that box. This region is kind of a rain fog region, and so this is saturation, or what would be 100% relative humidity. This humidity ratio is the mass of water vapor contained in the air divided by the air mass, and we can't exceed this line. At this point, the water wants to condense into a liquid phase. And so this is where our weather is. If we look at that envelope plotted, say, on Denver, Denver's just a lovely climate, and you can see that Denver rarely gets to the humidity levels that we experience here in the Midwest. It rarely gets colder than what we get to experience here. It has some drier climate, but there's some things you can do, such as evaporative cooling, to stay comfortable at these higher ambience. And so it's just a lovely climate. Burlington, Vermont, yeah, it's a real tough winter, typically. They don't have the summer conditions that we get to enjoy here with nice heat and humidity. And while they do have more cold weather than we have, it typically doesn't exceed what we see here in central Illinois. Miami, just the opposite. Not much of a winter, but you know, they get up to similar humidity levels. They do that more than we do, but we get to experience that. And then finally over here in Seattle, Washington, again, another lovely climate, but maybe a little bit dreary during the rainy season, but not so much the extremes as far as high humidity and then very cold temperatures. And the main point about that then is that I'll use our weather as an example on the characteristics of HRVs, ERVs, and then a smart ventilator or a heat pump ventilator as we manufacture, just because we span such a broad range. Now, if we take an HRV and we're considering winter and what happens in an HRV, if we take air at this condition, this would be air that's, say, in a home that's about 40%. In many of the high performance homes, we'll often see 40% without active humidification within the home. My home throughout the winter is typically 40 to 50%. We have about 40 to 50 plants scattered through the house. My wife is a wonderful cook and regularly cooks, and so we have other things that add moisture in addition to our respiration and washing activities. We take this air and we go through an HRV. It's going to cool down as air from the outside, let's say 20 to 30 degrees, and you can see that the difference between low humidity and high humidity on an absolute moisture basis is not a very big difference. And most of the weather in most winter conditions, whether it's 100% or 50% humidity, relative humidity outside, it's not a big difference in the moisture level as we get to these cold conditions. So just saying we're in the 20 to 30 degree range, this air warms up as it goes through an HRV core as the air from the inside cools down. Now, as the air is cooling down, if it hits this 100% relative humidity line, further energy coming out of this air is also going to come out in the form of condensing water. The humidity, if it's high enough as it cools down, will finally hit saturation, water will condense. Depending on the HRV, some HRVs avoid that condition like the plague. They don't want water in their core. They don't want to have to put a drain pan in. And so one of the things that distinguishes, say, a high-performance HRV from a lower performance is whether it has a drain pan. So a higher performing HRV needs to deal with this condensation because it will be a frequent condition in other cases. Now, the air coming from the outside, it won't go all the way up to comfort conditions. Depending on its efficiency, it will come up to somewhere less than comfort as the air from the inside drops down somewhere not quite at outdoor air temperature. It comes in at a lower humidity, typically in the winter, and so this increase in moisture, this is from you and your metabolism and your showering and cooking. And depending on how much moisture you generate into vapor and determines how high you are, what your indoor relative humidity will be. Now, as we cool down further and we get below freezing, many HRVs will have a preheater, an electric heater, that will warm up the air. And obviously, this is a very energy inefficient thing to do before it goes through the HRV to do some energy recovery. Other HRVs will try to avoid freezing in it by recirculating or lowering the ventilation rates, which is a bad thing to do because we need just as much fresh air in the winter, if not more, as we seal our homes up as we do at other times of the year. If we look at an ERV, starting at, say, about the same condition, this is a little bit higher humidity, say 50%, because one of the characteristics, as we'll look at, is that an ERV is recirculating moisture. So as it's going through its exchanger core, it's dropping in moisture level as moisture is coming out and going through the permeable core and going in the outside or the fresh air stream. And so this is picking up in moisture level as it's angling up, as we're then dropping moisture level on what's dropping. Again, we don't quite come down to outside conditions as we don't quite come up to inside conditions. We have the same problem with freezing, that these cores, you definitely want to avoid freezing in these small passageways. They're not frost tolerant. Often it will destroy the core as well as just blocking the airflow. And so various mechanisms, the same as described for HRVs, are employed. When we go to hot weather, it's the opposite, but a similar type of effect. Let's say our inside is maybe at 75 degree and maybe about 50% humidity, and outside maybe about 90 degrees and 50% humidity. But notice that 50% humidity, relative humidity, is a much different amount of moisture. So with an HRV where we're not transferring moisture, we simply see the air that we're moving through the core getting hotter and the air from the outside getting cooler. The air coming inside isn't making it to comfort condition, but it is recovering or exhausting energy that's a benefit. Looking at an ERV, in a similar manner, the ERV, as in the winter, is going to exchange energy. And if the outside is more humid than the inside, then we will drop the moisture level, which is a benefit of the fresh air stream, as that moisture is transferred into the exhaust stream. But what often happens within our homes, we typically want to exhaust from kitchen and bathrooms, which are very moist areas. Imagine taking a shower, your towels are wet, the bathroom walls are wet, and there's moisture on the mirror and on windows. This is a very humid environment, and as the air moves into the bathroom and is exhausted, this will often be above, even in a very humid condition, the humidity level from the outside. And so what we will find is that this outside air in a humid situation will come inside even more humid because it's getting moisture from this very humid exhaust air from the inside. And I have a reference here to a study that Joe Stabrook with Building Science Corporation conducted a few years back in Houston, where they found this effect to be true. So this takes us to which is better, an HRV or an ERV? And from detailed simulations we have run, and I'll show you more results as we compare the smart ventilator. But for, say, a typical home, a 2,000 square foot home with 2 to 4 people and typical activities, HRVs, energy-wise, would perform a bit better here, and ERVs in, say, more humid regions would perform better in those areas. Now let's look at a smart ventilator, a heat pump-based ventilator, such as what we work with, what we manufacture. When we are in cold weather, we'll take inside air, cool it down, and then we like to condense, and we also like to freeze that water that was inside of the home, because that condensing and freezing is energy that we can convert into sensible heat. And so as this heat is put into our heat pump, the heat pump takes outside air and it warms it up. You don't see a moisture change in the air because it's a sensible heating, and it can end up warmer than the inside air. So it's coming in at comfort conditions or higher on average. And when we look at summer, whether the inside air that we're exhausting is lower in humidity or higher in humidity, because we don't connect up the air from the inside to the air from the outside, that as air from the outside is passing through the cooling coils of the heat pump, it then can hit saturation, and we condense and dehumidify that air. And the heat from the cooling and from the dehumidification is put in the air that's being exhausted to the outside. And again, you don't see a moisture change in that as we pass to the outside. If we compare this C as a smart ventilator or serve-like ventilator with a heat pump with an HRV and an ERV for these different regions, basically what you find is that a smart ventilator that on average is bringing in the same amount of fresh air, but the reality is it's bringing in more fresh air when you're there and not when you're not there. That it has better energy performance throughout these different climatic regions than an HRV or an ERV. Now you can see what I discussed before. Here in Atlanta, an ERV would be a better choice than an HRV. Here in Central Illinois, it's kind of a toss-up. We're kind of on this border. Going up to Burlington, you see an HRV being a benefit over an ERV. And so, so typically ERVs and HRVs do have this boundary of operation, but employing a heat pump that can actually condition fresh air as you're bringing it in, as well as contribute to the conditioning of the home at other times, that the energy performance can be improved overall. This is just a plot of relative humidity within a home for our climate with smart ventilation, HRV, ERV with 4 people. And this is using our simulation model called Zeros. And if you have an interest in using this, it's a free-to-use online house design software. It looks at not only the energy of home design as other energy models, but also the indoor air quality along with the economics and financial monitoring for homes. You can see that an ERV will result in, say, a higher average relative humidity in the winter, but it also keeps the humidity higher in the summertime as well. Because a ventilator such as a serve separates the incoming and outgoing streams, its humidity is somewhat similar to that of an HRV, not very different between the two. And the reality, as I mentioned, in our home, we're typically at 40%. Depending on what other additional moisture you add through cooking and plants and other activities, that you may naturally keep it at a, say, a more desirable humidity. I want to make the point that high performance and smart ventilation, good energy performance are not two different things, and here's just kind of a sampling of a wide array of homes in very different climates. This is a Vermont home, the one that report is written on, with a lot of detailed air quality, comfort, and energy data in the report that we wrote. And just a little bit more detail, just as far as the actual energy differences. While the smart ventilator on an energy basis from our modeling is shown to be more energy efficient, I want to make the point that this, say, 500 kilowatt hours per year, that's $50 or so of energy difference. It's not a lot of energy cost difference. The real value is in your indoor air quality and how that makes you feel, how that improves your health, how that helps you function. Let me just point out one other thing. We've seen this a couple of times in homes where our systems are installed. Here's a new house up near Chicago that had a gas leak. This is the VOC level. You can see how it's much, much higher than the CO2 level. And the CERV was doing a lot of ventilation to try to keep the air as fresh as possible. They finally tracked it down as they saw these very high VOCs. And once the gas leak was fixed, and I want to make the comment that we encourage these folks to not put natural gas in their home, but it's a tough sell still. There's other reasons why it's not beneficial in addition to problems like this. But once that was brought into control, you see how VOCs and CO2 interplayed with each other. I won't go into this. We have a webinar that's posted on new indoor air quality metrics to help us better understand how the air quality we maintain in our homes makes us feel better. But you can find more information on this on our website. Let's talk briefly about the future. This is really it. Energy is really a constituent of our real goal, and that's for us to feel healthy and comfortable. We want to feel good. And what I started calling pre-ventilation, but just a concept that we can do better than ventilation. We can sense and prevent poor air quality, or we can pre-ventilate before needed in a manner that we can efficiently, say, keep air quality knowing that an event's going to occur. Right now, we're at this area where within a smart ventilator such as the one we build, online, someone can look at the status, control, perform diagnostics, and then access all their archive data. And in the future, now we've already developed what we call CERV analytics, but trying to help us in a similar manner with activity trackers and other biometric monitoring devices, just see how this data can be used to make us feel better. But as we look at big data and artificial intelligence allows us to, say, correlate or find linkages between disparate types of data that are difficult for us humans to maybe find the linkages. For example, trying to predict what a stock is going to do. These large computer algorithms, sophisticated computer algorithms for following the stock market are using artificial intelligence for trying to find these linkages that that may occur between this stock, that stock, this business sector, and that business sector that may not seem related, but can help predict whether a stock is going to increase in value or not. Similarly, in the medical field, taking this symptom and that symptom and this occurrence and that occurrence and trying to figure out what may be wrong with us by linking things together that are outside of our range of vision or ability to link. So our vision our goal is to see how to use this data that is being collected within the served community and link it to other things such as outdoor air pollution and pollen reports, other systems and their operation within our homes, and these powerful algorithms for linking all of these things together to try to make us feel better. If we can use a smart ventilation system to identify when we might be liable to have a migraine headache in a day or two, or have an asthma attack, or a sinus attack, or our arthritis, how to minimize arthritic pain. We can save a lot of money as well as pain and suffering, and we're confident that this is going to happen and it's going to improve our lives. So to summarize, Florence Nightingale knew this 150 years ago. We need to better ventilate and make it a high priority in our homes. We need to not leave where the ducts go to the trades to just come in helter-skelter and fight with the plumbers and the electricians to make their runs, and then to have to cut through every stinking 2x4 stud in the building to get ductwork from here to there. We need to design this in, and we need to design it in a purposeful manner, the same way our lungs and our trachea have been designed into our bodies. It's very important. Smart ventilation, it moves beyond just thinking in terms of a simple fan and a ventilator. This is to give us a peace of mind, to improve us in body and spirit, to give us the confidence that our home really is healthy, because our noses aren't going to be capable of doing that. And then finally, let's move on to maybe an era of pre-ventilation. That smart ventilation in many different ways will help reduce our probability of getting sick, help us feel better, and do this in cost-effective manners. So I thank you very much for your time. Here's a list of references to get you started. There's dozens and dozens more, and our newsletters also contain a number of these. And so I'll take a look and see if there are some questions I can answer, but please feel free to post some questions as well as contacting me afterward. Thank you.
Hey, thanks, Ty. And yeah, we got a lot of questions piling up here, and feel free to throw some more in there. We got some time to answer questions. Before we get to those, real quick, for those of you looking to get your continuing ed, when this session closes down, a survey will pop up. Take that survey. Also check your email for reporting requirements. If you're watching the recording on demand, make sure to take your 10-question quiz and complete with an 80% passing rate. And overall, I have to say a huge thanks to all of our sponsors who allow us to do what we do. Sun Intuitive Self-Tinting Glass, Niagara Conservation for one of the lowest flowing, most affordable toilets on the market, Build Equinox Serve, Certainteed Air Renew for Meldehyde Eating Drywall, and Panasonic Ventilation for all your bath vent ventilation needs. Those of you looking for continuing ed under the Passive House program, you can earn one certified CPHC at fias.org/CPHC/self-report. Enter the code 12355. Also, for those of you joining us live, you will get an email with a direct link to that. So some of the questions, we got a lot of questions coming in. There were a few that really stuck out to me. I think heading back to ASHRAE and this concept that ASHRAE is not enough. There actually have been, there's been a lot of thought, even I think from the Building Science Corporation community is one you had mentioned, Joe, that actually the 62.2 standard might be too much. Now, I just wanted to get back, when you say it's not enough, are you maybe not necessarily saying always that ventilation rate being the requirement when you say not enough, but that you're thinking of ventilation in other ways other than just a standard straightforward ventilation rate?
Yeah, so there's two aspects, and I think maybe the best reference is your webinar, in which you had Professor Allen from Harvard, Dr. McNaughton from Harvard, and so anyone in the audience interested in more depth on that, Harvard School of Public Health is at the forefront of developing this information on how carbon dioxide, previously thought to be benign, very much impacts our cognition capabilities, and how, in general, doubling the ventilation in occupied areas from about 20 CFM to about 40 CFM per person is important. But the other aspect relative to your question is that, you know, maybe 20 CFM is okay if you're in your house 24 hours a day, but what happens is that there's a lot of people in the house for a certain part of the day and then not so many in for another part of the day, and the ventilator just keeps continuously running, isn't bringing in enough fresh air when it's needed, and then isn't closing down on the ventilation level when it's not needed. And so those two aspects are what a smart ventilator can address. Supplying as needed based on the activity level and number of people and when they're there. It just automatically takes care of the scheduling. As I go down the list, I see. Go ahead,
I was going to say, Ty, another thing that's popping up here, that's bundling up, is this question about. Well, first of all, let me kind of ask kind of two questions here. Can you talk to us about how many different smart ventilation systems there are on the market? Are there conventional HRVs or ERVs that are maybe designed so you can have them as smart system? And then second to that, does a smart ventilation system, does it have to be integrated with a heat pump, or is that just sort of an optional aspect to make it function to the levels I just saw those questions, and yeah, let me address that. First of all, I know that there are ERVs and HRVs where you can then add, say, a VOC or a CO2 sensor that will trigger it to higher ventilation. And so that's available. I am not aware at this point, but if anyone out there is aware, and I appreciate a note, where there are other, say, fresh air systems that automatically build that into the system, and where the data is archived. But let me also make the point that with like once through ventilation system, say these constant flow ventilation systems through a home, if you put a CO2 or a VOC sensor, say, in the living room, and there's a lot of people in the living room, so it goes up and it starts telling the HRV or ERV to increase in ventilation flow. That's going to happen throughout the house, and so while it may bring the CO2 VOC down in that occupied room, all those unoccupied rooms are having a higher level of fresh airflow through them that isn't being used. And so you get a higher level without the effectiveness of making use of that fresh air. So recirculation, the value of that in a smart ventilation system is that we are sensing the return air, so the bulk combined, and keeping the whole house as uniformly as we can at a lower level of CO2 and VOCs. And what this amounts to on a practical basis in most homes is that about 20% of the time we'll be in fresh air ventilation at about 150 to 200 cubic feet per minute. And then about 80% of the time we're recirculating, and whether or not there's conditioning added to it, additional heating or cooling dehumidification. But I will, along those lines, there's no reason why there couldn't be a smart ventilator that is based on an HRV or an ERV core. And in fact, there's some in Europe that have both, like a heat exchanger core along with a heat pump, versus the heat pump, as in our case, which we also have developed because it significantly contributes to comfort. I hope that kind of addresses that. I wanted to mention, I see a question here on the source for respiratory illness doubling.
I don't know if I have that source on this talk, but in our February newsletter article on this subject, I definitely have that reference. It's from Professor Milton at University of Maryland, where I believe I have a couple of his articles. He's very much at the forefront of how airborne diseases are spread. But it's an article where he and his co-authors are describing how better ventilation engineering can improve, can reduce illness and sick days in buildings. And so our February newsletter will have that.
Great, thanks.
Mm-hmm.
Oh, I was looking at this question here from Mark on the mentioning the smart ventilator in the winter lets moisture freeze. What do you do to deal with ice in that regards?
Oh, okay. Yeah, I didn't get to that one or see that one, but so we have a defrost algorithm within it. It's one that makes use of the heat pump. It's not an electric resistance, but similar to say a mini split going in defrost mode, these cold temperature mini splits, and so so we're able to defrost as needed. And as you saw in that Vermont data that I showed, those homes all have our smart ventilation system in them, and you saw them operating in temperatures down to -10, -20. We've collected data from one home where it got down to -26 Fahrenheit. And so we absolutely know that we're able to manage frost without sacrificing fresh air ventilation in as harsh of a winter as you might find in the U.S.
Can you speak a little bit about just briefly, the cost comparisons, as well as the maintenance comparison, and don't leave out the maintenance of the sensors of smart ventilation versus HRV versus ERV?
Yeah, that's a good point. Let's say, and you can contact us to get detailed cost information, but the serve nominally is about $5,000 for the unit cost, and let's say typical HRVs to ERVs might range from $1,000 to $3,000 or $4,000, and then there's whatever duct installation costs, which vary all over the place depending on if it's linked into a central system versus has its own duct system installed. As far as the sensors, we are among the first to incorporate these sensors. For example, the VOC sensor that we use is one that Honeywell now uses in their system, but we used it before they started using it. But we took that as a good vote of confidence that we had picked a good sensor, and we have been running these sensors for about 6 years now. It's hard to say accelerate the aging process on them. So yeah, we watch them very closely to see if they're going to deviate or have problems. But at this point, knock on wood, they all look great. But we're prepared to take care of them if they don't. But it's at the forefront, and both these sensors that we use come from very well-established companies. They're at the forefront of these technologies, and I can state that to date we haven't seen any sensor failures, and so we're as well as problems with the sensors deviating or getting way out of range. Did I?
Yeah, great, thanks. Another question here about the system being integrated with split system, duct system, or does it have to be a standalone?
Yeah, so on our ventilator system, the heat pump and what we call the fresh air module are two boxes that are about the size of a dorm refrigerator. Usually they're stacked one on top of the other. Sometimes they're placed side by side. But the fresh air module has some thermally broken bidirectional dampers that allow us to go from, say, heating or cooling mode, as well as fresh air and recirculation mode. And all the sensors and brains, the controller, are built within the fresh air module. And then the heat pump module is just simply the heat pump. It's an inverter drive heat pump with a variable speed heat pump, very high quality compressor in the heat pump. And it's one that we manufacture here. We build the heat pump ourselves. We design the controls. There's absolutely no finger pointing if something goes wrong with it. We've designed this thing from scratch. And so if there's a problem, you know, we're the ones to contact, not some other party. So you basically stack the two boxes, hook up the ducts, and connect the wiring. Now, $5,000 versus, say, $1,000, you know, if things are tight, you know, get fresh air in whatever manner. But we really feel the value of actively controlling air quality and what this means in terms of our health and what this means in terms of our productivity, that's where the real value is. And if you are more productive, say by $5,000 per year or $500 per year, and if you have fewer asthma attacks or are able to reduce your asthma medication or become sick less often, the dollars associated with these are just tremendous. And these are often dollars coming out of our pocket. And so so this is where we feel that the cost justification is for it. I see a question also listed here on how much skin we shed. The reference that I use in that from our January article on particulates is about 1 pound per year. Now, a lot of that is not, say, airborne. You know, it's in our clothes, on our beds, you know, places like that, or just bigger flakes that fall to the ground. But a fair fraction of that is in the air, and I'll give you one good reference for that is Brett Stevens, who's a professor at Illinois Institute of Technology. He has a couple of wonderful presentations on his site that I highly recommend on particulates. And one of them where he's looking at the genetic material of the biome within various homes. The most prevalent one has to do with bacteria that are on skin. And basically the takeaway from that is that there's skin particulates everywhere throughout our house, and they very much are a significant part of those particulates. Why that matters, dust mites tend to feed on skin, and the excrement from dust mites for those with asthma sensitivities, this is very much a trigger, and so it's something to be aware of.
So a great question came in, and I'm really glad it came up. It kind of pointed to some of the lead application that I wanted to bring up here. And that was the specific question was, I have been looking for actual studies and data on what an applicable level of VOCs, CO2 in the indoor air should be. So I wanted to go off of that, and I'm really glad you brought that up, because it actually brought up a whole other credit that I didn't even think about. The first one that we had referenced at the beginning of the session, which was under IEQ contaminant control, one of the options is the pre-occupancy flush that we recommend during the session. So, you know, running the system after you construct the building to flush out any of the potential VOCs. But if you want to go all the way, you can use option 4 under that program called air testing. We don't ever see anyone ever use this option just because of the cost of bringing in the industrial hygienicist. But it does make me think that maybe a system like this, if it's measuring formaldehydes, particulates, ozone, TVOCs, carbon monoxide, if it can measure all of that constantly and showcase that, you know, the home is actually under the certain thresholds that have been set by the USGBC in this program that perhaps, this could also serve for the air quality monitoring system. But so anyway, to the question, I don't know if there's any, and Ty, you can jump in here after I finish up, but I don't know if there's any necessarily agreement, but I know USGBC in the V4 program under the air quality testing has tried to come up with some limits on these different pollutants in the air. The International Living Future Institute for the Living Future program actually requires that certain limits be hit within the session, but I think what they've all done is they've just found a target and they just shot at it. And I'm not so sure how much data goes behind that, but anyway, I'll be quiet now and kind of hand that off to Ty.
Yeah. So yeah, that's a very sophisticated test. And we're not seeing, say, cost-effective sensors or ones that could practically be used as a smart ventilator to dissect to different components like that yet. But I'm confident those are going to be coming along, and as they do, we're for sure going to be incorporating those. But let me say that, for example, the total VOC sensor we use, that sees anything that's a reactive substance, so ammonia, carbon monoxide. Carbon dioxide is essentially an inert gas, so the VOC sensor does not see carbon dioxide in the similar sense that the carbon dioxide sensor does not tend to see VOCs. There's a few gray areas, heavier organic gases like a refrigerant that might show up on both, but things like formaldehyde don't show up on the CO2 sensor. So while we can't discern those, just a couple of notes. One is that we definitely do see formaldehyde, and in one of the early Vermont homes, these manufactured homes that we're involved with, the first 4 homes that were built, 3 of them looked identical. The 4th home just had VOCs coming out all over the place. They weren't occupied yet. They were just, just been built, and they were just, under shakedown. They tracked it down to a countertop, a Formica countertop, that all of the countertops had been ordered as no VOC particle board, and one came in damaged, and when the replacement came in, it was not replaced with the same no VOC particle board. And so it was just off-gassing, and we were picking that up. They replaced that, the VOCs went down. But it would be nice to be able to identify individual components so that we can see what that source is. Now another, and I think that'll happen in the future. Another thing is that there's now wall board. I think Georgia Pacific has a wall board that absorbs VOCs, and our initial experience with that passive house level home built up near Chicago that used it, we thought our VOC sensor wasn't working because we had never seen a new house, even a conscientiously built home with low and no VOC paints and furnishings and materials. It just was not showing any increase in VOCs. But then when they started leading tours through as the home was, as construction was built and they opened it up for tours in the community, we could see VOCs from all the people activity in it. But it really was absorbing VOCs in a manner we hadn't seen before. And so there's also, say, new things coming along that might be able to absorb and break down VOCs while they're being developed. I saw a note here, or a question somebody asked about reduced flu rates relative to ventilation rates. And the reference for that is also from Professor Milton, but from an earlier study that he did with some colleagues, where they studied, I think it was about 100 buildings or so, and this is also linked in the February article. But this was a study where they looked at over 100 buildings for a large corporation, Polaroid Corporation, about 3,000 employees, and they studied these several dozen buildings, and they classified them as high ventilation rate and low ventilation rate. They went in and took measurements and did the analyses on that, and they found that the absenteeism for things like flu and cold were significantly higher in the buildings with lower ventilation rates. And so that study, which again is referenced in that February article, that it very definitely shows that improved ventilation will result in fewer missed days of work.
All right, great, Ty. Well, it is now 1:30 here, so we definitely got to get wrapped up. But before we do, Ty, just again remind us of where people can contact you and find out more information and get all their questions answered.
Yes, contact us at Build Equinox, and be glad to answer any questions you have on this or point you in any direction for additional resources and references on this subject. Thank you very much.
Great. Thanks to Ty Newell. Thanks to Build Equinox. Everyone have a great week. Take care.